Hey, welcome to the TBM-850 SET class rating.
Wow, this is the best-looking aircraft I've seen till now.
Well, it comes with a hefty $1,500 hourly rate.
I think it's worth it. Look at that dash.
Okay, in this differences training we're going to touch on some of the different systems you're going to get used to, but we're not going to talk about the engine as that is the scope of the SET. Without further ado, the altimeter. The TBM-850 can cruise well into RVSM airspace. Historically, aircraft altimeters became less accurate when flying into the very thin air above flight level 290. This technological limitation kept the traffic separation at 2,000 feet in the vertical. With reduced vertical separation minimums, this vertical buffer can be reduced to 1,000 feet. This basically doubled the high and fast traffic that ATC could manage. The required equipment for RVSM is 2 independent altimeter systems, 1 automatic altitude control system, an altitude alert system, a secondary surveillance radar transponder linked to the automatic altitude control. This ensures safety while flying just 1,000 feet above or below traffic that is flying towards you. The TBM has a Honeywell AM250 digital analog altimeter with an embedded altitude capture warning system. The Bendix King KAS297B altitude selector is the heart of RVSM operations. You can select the target altitude for the autopilot and the altitude warning system, but you can also select a vertical velocity to get to that altitude by pulling on the inner knob. Do not forget about the engage and arm buttons. Up until now, the altitude capture was automatically armed. Now you have to press the arm button. The VS mode is engaged by pushing the ENG button. The altimeter shows altitude in digital form, and it can set barometric pressure in millibars and inches of mercury. There's also a standard push button to hastily switch to flight levels at transition altitude. The airspeed indicator is another departure from what you are used to. As opposed to the Duke and the Chancellor, the zero speed value starts from the 6 o'clock position on the instrument. All other airspeed indicators you've used started with a zero value at the 12 o'clock position. Thus, your important V-speeds are on the left of the dial while the maximums are on the right. The Electronic Flight Instrumentation System, or EFIS for short, is another big difference from what you're used to. The two displays show attitude indication and horizontal situation when the gyro system is powered up. This panel powers the entire gyro system. There is also a composite mode, where all the information is displayed on both CRT displays, mitigating a single display failure problem. The autopilot control panel is located right in the center of the dashboard. It has known lateral and vertical modes, but also some new ones. For example, the soft ride and half bank modes make the ride more comfortable on the passengers. The landing gear is electromechanically actuated, just like in the Duke and the Comanche. The Chancellor had a hydraulically actuated gear. The maximum gear extension speed is 178 knots. Do not retract it at more than 128 knots. Now, the TBM is a fast-flying aircraft. If treated poorly, it will kill you. To aid in minding your surroundings, the TBM has a HOTAS system installed. The Terrain Awareness and Warning System is a predictive system that looks in front of the aircraft and matches the flight path with any obstacle in the database. It then warns the pilot of incoming dangerous terrain. It also has a premature descent alert to warn the pilot that a steep descent was initiated too early for the next runway on your flight plan. The environmental control system is not very different than what you've already seen on the Duke and the Chancellor. The biggest difference is that the TBM-850 uses bleed air gathered from 2 stations inside the engine compressor. Depending on the regime, these valves open and close automatically, managed by a system called the Global Air System Controller. Because the gas generator can produce quite a lot of pressurized air even at high idle on the ground, the air entering the cabin can be cooled or warmed even at these conditions. The bleed switch on the panel can be off, which shuts off the common ECS valve. In auto, the system takes care of choosing which station will provide air for the ECS, minimizing engine power loss. In the high position, the system is commanded to open the P3 valve and take bleed air from that station exclusively. Talking about environmental control, a very important topic is the sealing of the cabin. The TBM-850 has a pilot door, unlike the rest of the pressurized aircraft you've flown, which only had the passenger door to seal up. Maintenance of the sealing system costs our school about $1,800 per year, and it is one of those systems keeping you alive. Any hissing or abnormal pressure readings of the cabin should be dealt with as soon as possible. As you saw, all openings are equipped with lock indicators. These are red-white if the locks are not in the safe position, and the gas won't inflate the seal to avoid a catastrophic failure at high altitude. Green-white means all locks are in the safe position. Another difference that you'll find in the TBM is the fueling system. The 850 has 2 wing tanks, but only one can feed the engine at a time, manually selected by the pilot. To avoid dangerous imbalance situations, the Daher installed an automatic fuel selector. On the ground, this selector changes feeding tank every 75 seconds, while in the air it changes tanks every 10 minutes. The pilot can manually tell the system to switch any time and the counters are reset. This selector is a low-voltage valve, so it does not drain a lot of electrical power when in operation. As I said, we're not going to talk too much about the engine, but bear in mind that the TBM reintroduces an engine trend monitor. This keeps logs of temperatures, pressures, and torque values and alerts in case of exceedance. It also helps the pilot in optimizing cruise by computing the mileage value. The low-voltage, highest ITT page is especially important in engine start as it logs the minimum battery voltage and the maximum ITT attained during the start. The ETM also keeps track of inspection times and USB storage occupancy levels. Another nice feature of the ETM is that it shows torque in absolute values, instead of the engine instrument on the dash that shows it in percentage of maximum. The unit of measure is pounds of force, foot. Besides the ETM roll, the unit can show navigation, fuel, and air data. And a last point I want to talk about is the propeller and the governor on the TBM. As you can see, the propeller blades are quite thick and the radius is quite large. Turboprop engines provide way more power than piston engines. Thus, this big, thick propellers can be used to create enormous amounts of thrust. The propeller is pulled by heavy-duty springs into the feathered position, so the governor has to work extra to force these blades into finer pitches. The oil pressure inside the governor can reach about 400 psi, instead of the 300 for something like the piston Duke. This governor also employs a proper beta range system. Piston engine governors don't employ beta ranges as the engine power output can be pulled down quite low and the engine will still rotate. In gas turbine engines, there is a minimum safe regime that will still keep the cycle going. This regime, coupled with a big propeller, will make the 850 slowly taxi in idle power. This consequently means that once the brakes are off and the taxi speed was reached, the aircraft will continue to accelerate even if the thrust lever is pulled back in idle. That would mean a lot of braking during the taxi, which will in turn make you change pads every week. That's a $600 weekly subscription. The beta range is a system embedded in the governor. When the throttle is pulled back past a certain detent, the governor locks the blades, mechanically at a maximum pitch angle of 21 degrees. Any further pull back on the power lever will result in the blades twisting further towards 0 degrees and even negative pitch angles, with a maximum at -11 degrees for full reverse thrust. Thus, in beta range, the pilot directly controls the pitch angle of the blades using the throttle control. This is in opposition to the normal operations where the governor automatically sets pitch angle to achieve RPM. We'll talk more about this during the engine management course, as there is also a reductor inside the engine to transform that high RPM in torque. A system you've not met before on piston aircraft.